Hey everyone, so let's solve this Leetcode hard problem. Maximize the minimum powered city. So, like the prerequisites for this hard problem would be you should be aware about prefix difference arrays, and since it's a harder problem, so you should be aware about like basic binary sets. Then only we'll be able to like solve this problem. Okay, so means both of these means the basics of both of these algorithms should be clear. Now let's move on to the problem statement. So we are given a zero indexed integer array stations of length n, where stations of I represents the number of power stations which are present in this ith city. Okay, now each power station can provide power to us every city in a fixed range. And what is this range? Suppose we are at ith city, so we are given this radius, so this ith city can provide stations means power to the range I minus r till I plus r. Okay, this is given. Okay, so each station I has this range defined where we are given this integer array r means integer r, and then the power station at city I can provide power to all cities j such that their means absolute difference is less than or equals to r. Okay, so the range will be simply from I minus r to I plus r. And then the power of a city is the total number of power stations it is being provided power from. So for example, since suppose a city is lying here, so it will be like getting provided power from some of the cities on the left as well as some of cities on the right. Okay, so hence the number of cities from which it is getting power, it is like means it will be the power of a city. Okay, now the government has sanctioned building k more power stations, each of which can be built in any city. So we need to build k more power stations, and we can build it in any of the cities and have the same range as the pre-existing ones. Means r remains the same, and we are supposed to build k more power stations. Okay, now we are given these two integers r and k. We need to return the maximum possible minimum power of a city if the additional power stations are built optimally. So here we need to maximize the minimum power of a city if like the stations are built optimally. So the problem is simply what do we need to do? We need to maximize the minimum. So I hope like something standard is means clicks in your mind, like how we'll be approaching this problem. Okay, and note that you can build the k power stations in multiple cities, so we can like we can build in whatever way we want. Okay, there is no restriction on that. So for example, if we have the stations as this, and we can build two more stations. So let's try to find out the initial power of the cities. What are the initial power of the cities? Okay, so we have the cities 0 1 2 3 4. So initially all the cities have 0 power. Now due to this 0th city, it will be having a range from 0 plus r to 0 minus r. So 0 minus r will be lying means outside of the range. 0 plus r simply means 0 to 1. So this city has means increased the power of this city as well as this city by plus 1. Okay, because the number of power stations in this city is 1. Okay, so it will be getting increased by plus 1. Now if you consider this city, it will be having a range from what means 1 minus r to 1 plus r, that means 0 to 2. Okay, so it will be increasing the ranges means the city power of these cities by a plus 2 value. So it will be increasing plus 2 plus 2 and plus 2. Now if we consider this one, then it will be increasing this range by plus 4. So this range is simply plus 4 plus 4 plus 4. Now if we consider this city, it will be increasing this range by plus 5. So it will be increasing plus 5 plus 5 and plus 5. Okay, I hope like this is correct. Let's see the given input. So the initial powers that we had, yeah, it is the same. And let's see, consider this. So this will be having the range of this. So it will be providing 0 cities for this. So it will be simply plus 0 and plus 0. So overall the initial power that each station will be having is simply 3. This is 437. This is 549 to 11. This is 549 and this is 5. Now what you can do is we can build two more stations, and we need to maximize the minimum power of any city. So currently the minimum power of city that we have is 3. So we need to increase it, right? Can we like since the next minimum that we have is 5, so can we increase its power to 5? Okay, so let's try to means we will be able to build two stations and we need to increase it. So can we increase it? I means we can simply build two stations here only. So if we build two stations here only, then the new power will be becoming the here it will be getting plus 2, here it will also will be getting plus 2. Okay, or we can build one means two stations in this position. So if we build 2 stations in the position, then also we'll be getting plus 2 here, plus 2 here, and plus 2 here, and the minimum that we'll be having is 5, which will be the maximum. Or in this case, can we build it any station here? No, because it will have no effect on this range, because its range is simply defined to this range. Okay, so hence what we'll do, either we can like build 2 stations here or 2 stations here, or we can simply like build 1 station here and 1 station here. Okay, so due to this 1 station at here, it will be getting increased by plus 1 plus 1 plus 1 at 3 positions, and due to this plus 1, it will be getting increased by plus 1 and plus 1. Okay, so we will be getting increased by 2, and finally this value will become 5. So the minimum value that we will be having is 5, and which will be the maximum possible after we have built these 2 stations optimally. So hence 5 is the output in this case. Okay, let's see another input. So we are given the stations as 4 4 4 4, but the r is supposed to be 0. That means the range will be simply from what? I minus r to I plus r. But r is simply 0, so that means the range of stations is simply I. That means it is restricted to itself only. Okay, hence the initial power that we'll have, initial power, it will be the same, means it will be this value only, which is simply 4 4 4 and 4. Now we can build 3 more stations with the same r, and we need to maximize the minimum. So obviously if we want to means increase the, since the minimum here that we have is 4, so if we want to increase 4 to 5, then all of these 4s should be getting increased to 5. Okay, that means all of these stations should be getting plus 1 power from like any of the station. But we know like this r is simply 0, so it will be this, means even if we build a station, its range will be limited to this station only. Since to convert the means the minimum value currently, which is 4, to convert it to 5, we need at least 4 stations, which will be built at here, 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 and here. So in these 4 positions, this 4 stations will be built, and then the minimum possible value, minimum power will become 5. Okay, but we can only build 3 stations, hence we can like get the final configurations as this only. 4, suppose 5 5 5. So any 3 of the values will become 5, and one will still remain the 4. So hence the minimum possible, like the maximum possible value of the minimum power of any city is simply 4 in this case. Okay, we'll not be able to increase it further. So obviously once like as soon as we read the problem statement, we identified that what do we need to do? We need to maximize the minimum. And to solve these kind of problems, to find the maximize the minimum, we'll obviously be using binary search, because this is the most standard algorithm to solve these kind of problems. We have like multiple algorithms, multiple problems like a book allocation problem, and like there are multiple problems which is like minimize the maximum or maximize the minimum. Okay, so these are like pretty standard. So I hope you are like aware about the basics of binary search and have solved these kind of problems. Then it will become much easier to solve this problem. Okay, so now to apply binary search, the first step is to identify the search space that will be having. Search space. Okay, so let's find out first the low. What will be the low? So we know like what will be the minimum power that we each and that any station can have initially. It will be simply what? It will be simply the minimum value of this array. Okay, the minimum power that any station can have, suppose r is equals to 0, so the minimum power that any station will be having initially, it will be simply the minimum value present in this stations array. Okay, so the low will be simply pointing to minimum of stations of I. Minimum of stations of I equals to 0 to n minus 1. Okay, now what about high? What can be the maximum power any station can have? Okay, what will be the maximum power that any station can have? So if we have like r is defined in such a way that each station is having the effect on each station, means this 0th station is having the effect on n minus 1th station. That means this r is equals to n minus 1. So this n minus 1th station is also having the effect on 0th station. That means each station is having the effect on all of the stations. In that case, suppose if we initially have the stations of I as the value, so this value will be increased by all of the stations. So it will be simply what means sum of stations of I, because it will be getting power from all of the stations. So it will be simply summation of stations of I, and we are given k that we can build at means k more stations. So if we build k more stations, then we can increase this power by k value as well. So the high value will be simply sum of stations of I plus this k. Okay, so we'll simply find out these two values. Low will be simply the minimum value in this stations array, and the high will be simply the sum of stations of I plus this k value. This is the maximum like power any station can have. Okay, and now we'll be applying binary search. Okay, so how will we apply the binary search? Suppose we have this mid. Currently we have the mid. Okay, now what do we need to say? We need to check whether after we have placed at most k stations, means after we have placed means at most k stations, the minimum power of any city should be greater than equals to mid. Okay, so what we'll do for this particular mid, we already want we can place at most k stations, right? So after we have placed all these k stations, then the minimum power of any city should be greater than equals to mid. Then only like means converting means this mid is possible as the minimum value. Okay, so this check value check function, I hope this is defined. So what you'll do, if like this check for this mid is true, so if it is true, that means what you'll have, we want to, since we want to maximize this minimum value, so currently we'll update our result by this mid value. And now do we want, what do we want? We want the maximum. So obviously we'll be moving the search space towards the right. So we'll check for mid plus 1 whether it is possible to get the answer at mid plus 1 or not, then mid plus 2 and so on, right? So we'll update the means move the search space towards the right, that is update low towards the right. And if it is false, means for mid it is not possible. So since for mid it is not possible, so next step we'll check for mid minus 1. So range will be everything reduced, because since it is not possible for mid, so it will not be possible for mid plus 1, mid plus 2 and so on. Okay, so it will be decreasing the higher end of the row search space. So it will be high equals to mid minus 1. Okay, so this is like the simple check function that we'll be having, and in this manner we'll be like the binary search that we'll be able to perform in log of the search space that we have. A search space is simply suppose a constant of high, so log of high. Okay, and now what can be like the maximum value of high that we can have? So maximum value of high will be summation of all stations of high, which can be 1e5 into 1e5, so 1e10 and plus k. So approximately it will be of 2e10. Okay, so it will be high can maximum go up to 2e10. So this binary search will be taking log 2 of 2e10, and it will be what? It will be 2 to the power 30 approximately. Okay, 2 to the power 30. Log 2 to the power 30. So it will be simply 30. Okay, so complexity is will be 31, 32 approximately. Okay, now how do we like the next step is to find out how we'll be checking this mid. How we'll write this check function. This is the next important step. So we like while we were solving the test cases, we saw like finding out these initial powers is important. Okay, finding out these initial powers, what are the initial powers of each station is important. And now once we have find out these initial powers, then we'll be trying to put new stations and then try to increase the minimum power that we have. Okay, so the first step is to check function. Now we are writing the check function for this particular mid. Okay, so first step was to what? Find initial powers, of each city. Okay, now once we have find out this initial power, means how do we find out the initial power, since n can go up to 1e5 here. So what we try to do here is means how we brute forcefully increased the power. We saw like the range of this means for I, the range is simply from I minus r to I plus r. So we iterate a loop from j equals to I minus r to I plus r, and we increase like power of j will be increasing by what value? We'll be increasing it by nums of I, means simply stations of I. Okay, so we'll be increasing it by stations of I. But obviously that will not be allowed because n can go up to 1e5. So this will be like 1e5 into the ranges which can go up to approximately 1e means into r suppose. Okay, r can go up to at most n. So it will be simply this. So approximately it will be order of 1e10, which will not be feasible. Okay, so we need to be able to update, means find out this initial power in like order of n. Okay, or n log n. So how will we be finding it? Then comes the the concept of prefix difference arrays. That's why I told you, like, means if you are already aware about it, then you might have already got the idea how we'll be finding out this initial power array. And if you have not, then I'll tell you like how we'll find. For each I, the left portion that we'll be having is simply I minus r. Or if I minus r is lying 0, then it will be simply max of I minus r comma 0. Okay, this is the left portion. And the right portion will be what? Right portion will be I plus r. And if it is lying below beyond n minus 1 index, so we can take the minimum. So it will be minimum of I plus r and n minus 1. Now what do we want? For all values from L to R, we want to increase these values by nums of I. Okay, we plus nums of I here, plus nums of I here, plus nums of I here as well. Okay, and after R, this should have no effect. So from L to R only we need to have the effect. So in this case scenario, what we'll do, we simply create the prefix array. What we do, this is the main simple concept of prefix difference array. We initialize all the values with 0. Okay, now what we'll do, since we want to increase at L, so we'll simply increase at L. So at L will be increasing. Instead of looping through all the values from L to R, at L will increase, and I at R plus 1 will be decreasing it. Okay, now when we take the prefix sum of this new array, this nums of I will be getting, now here it is 0, so 0 plus nums of I pref, so it will become nums of I here. Then here it was 0, so 0 plus nums of I, here also it will become nums of I, until here it will become nums of I. And as soon as we do this, prefix of I equals to prefix of means nums of I, means the value present at this plus prefix of I minus 1. So this will getting cancelled out, and R plus 1 it will again have 0 value. Okay, so hence in this what we will do, we increase at L. This is a simple concept of prefix difference arrays. We'll increase at L and will decrease at R plus 1. Okay, so at R plus 1 we will be decreasing. Now once we have done this for all the indices from 0 to n minus 1, in the end we'll simply take the prefix sum. Okay, and once we have taken the prefix sum, this prefix array will be storing the initial powers. Okay, initial powers by means increasing in the range, increasing elements in the range. How will be increasing? Simply prefix of I will be getting increased by prefix of I minus 1 for all I greater than equals to 1. Okay, so we'll do that, and we'll be, now this prefix array will be storing the initial powers. Now once we have these initial powers, what do we want? When we are iterating through, we have the initial powers. Now we'll simply iterate through the array. Okay, now if we are at this ith station, and this ith station has the initial power of I, if it is less than mid, then we need to increase the power at this station, right? We want to increase the power at this station. And how will increase it? Since we have k stations to place, we will be placing some stations such that this value is reaching this mid, because at minimum we want to make this value mid. So we'll be utilizing the stations effectively, and we'll be placing how many? The deficit that we have here is simply what? Mid minus init power of I. Okay, so this is the deficit here that we have. This is the deficit that we need to fill here. Okay, so how will we fulfill it? If the number of remaining stations that we have is k, so if this k means the deficit that we have is less than k, means if this deficit that we have is less than or equals to k, then we'll be able to place some stations and increase its value to mid. Okay, and if it deficit is greater than k, then we know, like, even if we place all the stations at this particular I only, we'll not be able to increase its value to mid. So in this case, we'll simply return false, that it is not possible. Okay, so I hope this scenario is clear. Now how will how will we be putting these stations when this value is there? That is, the deficit that we have is less than or equals to k, and now we need to increase this init power of I to mid. So what is the most optimal way of placing this deficit number of stations? So obviously, since we need to satisfy for this I, and we have reached this particular I, that means we have satisfied the requirements from 0 to I minus 1, right? We have satisfied the requirements from 0 to I minus 1. Now we need to satisfy for this I. So you might think, like, we can simply place all the stations here. all the stations here, and means it will be good, means all the deficit will be done. But it will be means if we place here, then the range will be simply till I plus r, means till this range, or means it will have means it will be getting increased by plus of deficit. And since the previous doesn't matter, because previously we have already increased, means we have already satisfied the requirements from, since we have reached I, that means we have already satisfied the requirements for previous elements. Okay, so now if we place an station here, then it will be increasing the number of station power of values from this I till I plus r. But can we, means we see like this, these values which was from I to I minus r, these additions are getting wasted. Okay, because there is no need of adding it here. So what if instead of placing a station here, we place the station at this I plus rth position only? If you place the stations at I plus rth position only, then it will be increasing the ranges from I plus r minus r. So this will be till I, and it will be till means I plus 2r. Okay, so if you place deficit number of stations at this position, then all means all the powers in this range will be getting increased by deficit. Okay, plus deficit. So since means we, what do we want, we want to place, means since we only have k stations and we want to increase the value as much as possible, so obviously we'll be putting it in as efficiently as possible, so that it is increasing or means as maximum values as possible. Because if we place it here, then we'll be increasing the number of, means the, it will be increasing the stations, power of stations till this I plus 2r, but initially it was only increasing this till I plus r. Okay, so now it is having an extra addition for this range. Okay, so obviously like putting all the stations as I plus r is the most feasible. And now when we put at I plus r, we know like for all the ranges from I to I plus 2r, the number of like the power will be getting increased by plus deficit. Okay, so how will we like once again we have the move, means we can loop for j from I to I plus 2r and increase all the values from this range by plus deficit. Okay, we'll increase the initial power by this value. But obviously it will not be feasible, because for each I we can do that, and again it will be like the same concept that we were doing to find the initial power. Same complexity will hit the n into r, which will be going till 1 in 10. Okay, so again here also we need to use prefix difference arrays. Similarly, as we used to calculate the initial powers, since again we saw like we need to increase the values in this range, and for increasing the values in the range, what concept we use? We simply use prefix sum, prefix difference arrays. So again what we'll do, we'll increase here by plus deficit, and what we'll do, in decrease here by minus deficit. Okay, so when we reach this I plus 1, what we'll do, we can simply maintain the current prefix sum that we have in this deficit array. So instead of just simply checking whether this initial power of I is less than min, we need to check whether this initial power of I plus the accumulated sum that we have got so far. Accumulated sum, which is simply the sum of the increase or decrease that we have done previously. Okay, so the accumulated sum that we have got so far, we'll check for this, means the total additions that we have, means we have installed some stations previously and it is having the effect till at ith station. So we'll be having this accumulated sum, is by what value these stations are increasing the number of powers at ith station. So if this initial power of I plus the accumulated sum that we have got so far is less than mid, then we'll be nice, then we'll be finding out the deficit by taking the difference, and means everything will be modified. Okay, so just means initial power was not sufficient because we will have installed some stations before, and it will be having an effect at the ith position, it will be increasing it the power by some value. So we need to identify that as well. So and how will be increasing it? So we can simply also create, initially we created this vector prefix, we can create an added power. Okay, added power of n again, and what we'll do, we when we are at I, if we are installing the station at I plus 1, means I plus r, so it will be having the effect till I plus 2r. So what do we want? We want to increase at I we want to increase by plus deficit, and at I plus 2r till I plus 2r we want to increase. So hence at r plus 1 will decrease. So at I plus 2r plus 1 will be decreasing it. Okay, so this is the same concept that we'll be using. We'll be increasing added power of added power of I by this value and decreasing the added power of I plus 2r plus 1 by this value, and maintaining the current accumulated sum that we have got so far. At each step we'll be updating it by the added power of I, will be increasing it, so that at each position the current accumulated sum stores the means the extra power that we have got by installing new stations. Okay, so this is the means the entire algorithm that we'll be using for this check function. We need to apply the concept of prefix difference arrays two times. First, to calculate the initial powers of each station, and once we have got the initial powers of each station, then we'll try to place these k stations. And the most effective way of placing these k stations for satisfying the requirement for station I would be means placing it at I plus r, so that it covers as much range as possible, means it does not cover any redundant range, for which means for this I minus r we have already satisfied the condition. So that means increasing here was not means was redundant only. So that's why we try to fill means place stations here, so that the maximum range we can be increased, and then means we'll be able to like satisfy the requirement efficiently, or we are placing the stations optimally. Okay, so we'll follow this simple approach, and at each step we'll see like whether if there is deficit, then if deficit is greater than like the number of stations that we have, then we'll simply return false. Else we'll means install deficit number of stations, decrease the value of k accordingly, and if we are able to satisfy for all k, then in the end we'll simply return true. That means it is possible. Okay, so I hope like the entire logic for the check function as well as how we try to apply binary search for maximizing the minimum is clear. Now let's try to see the code for this approach, then it will become much clearer. Okay, so first we find the low as well as high. So low is simply the minimum element of this stations array. High is simply what? The sum of all the elements of stations array plus k. So it will be k plus all the elements of this station array. Now we initialize the answer with 0 and the we have mid. Now we'll be finding out the mid with simply low plus high minus low by 2 to avoid integer overflow issues here. Okay, then we'll check for this mid whether it is possible. Okay, if it is possible we'll update answer with mid and move the range towards the right, since we want to maximize it. Okay, so we'll moving low towards the right. If it is not possible, then that means it is we'll need to move towards the left. Okay, so we'll be doing that. Now once we have it, now how do we see this possible function? So possible function, in possible function what we'll do, we'll first find out the initial powers, then we'll calculate an added power vector to store the means the prefix difference of the stations that we are means installing in new fashion. Okay, and then we'll be maintaining the accumulator sum so far. So what we'll do, we'll have built a difference array for the initial configuration. Okay, so stations I adds powers from I minus r to I plus r. So we'll increase at I minus r and decrease at I plus r plus 1. Okay, so we'll have the initial power of size n plus 1. It means we can have it n as well, but then we need to check whether right plus 1 exists or not. Okay, so we'll have the left as well as the right. Then we'll increase at left by stations of I and decrease at right plus 1 by stations of I. And in the end we'll check means do the prefix sum, so that now this initial power can means stores the power of each station I. Okay, now we again use this added power to store the prefix differences of the new stations that will be adding. Okay, so the deficit that will be increasing at I, and I plus 2 plus r plus 1 will be decreasing at that end. Okay, so we need to store it in this added power array, so that when we are traversing through the array and we have increased at I plus 2 plus r plus 1, we have decreased it. So when we are doing the accumulator sum, we have reached this value. So that the current accumulator sum, if it is very large, it gets decreased, so that it becomes the real value. Okay, so this is what you know. So current added power that we have initially is 0, because we have not installed any stations before, and the stations needed is simply 0. Okay, we have not installed any stations before. Now the current added power simply increased is getting increased by added power 5. This is the same as the prefix sum that we do in this thing. Okay, so the same thing that we are doing it by storing it in this variable. So the total power that we have currently is initial power of I plus current added of power of I. Now if this total power is less than mid, then we'll need to install some stations and increase its power. Okay, so the deficit that we have currently is simply mid minus total power. Now if this deficit is greater than the number of stations that we have, means the number of stations that are left, so stations needed plus the deficit, if it is greater than k, that means we need more stations than sanctioned k. So we'll simply return false. Else if the number of stations required is lesser, then what we'll do, we'll increase the stations needed by this deficit, as well as the current added power is will be getting means at I will be increasing the current added power by deficit. Okay, plus deficit. And at I plus r plus I plus 2r plus 1, what we will do will means decrease it by deficit. Okay, so that this current added power when it moves to I plus 1, it will be having the means the prefix some values. Okay, so this is what we do. And if the means if we are able to process all the stations, all the cities without returning false at any step, that means we are able to utilize means place at most k stations and satisfy the condition, so we'll simply return true. And this will be like the check function with the time complexity of order of n, because we have used like this takes order of n, and all the like increase of the intervals means increasing values in the intervals we are doing in constant time by using prefix difference arrays. So this is like the most optimal approach to solve this problem. So the overall complexity would be, since the time means this will be taking log 2 of high, and the check function takes order of n, so it is simply order of n into log 2 of I, and this will be like approximately 30, so it will be 30n, and n can go up to 1e5, so this will be like approximately 1e6 to 1e7. Okay, and which will be like getting passed efficiently under 1 second. So I hope you were able to like see how we tried to first make an observation that we need to apply binary search just on the basis of problem statement. As soon as we read that maximize the minimum thing is there, we can definitely think of binary search. Okay, maybe means it is correct or not, we'll identify later, but we saw like the check function is like monotonic. It will be giving true values for a specified range. After that it will be giving false values. Okay, so this is what we identified, and then we are able to solve it. So let's try to submit this code here. This is the same code that we discussed, and this will be getting accepted because the complexity is order of like approximately n log 2 of 1e9. So it runs in like 243 ms, which is like pretty optimum, but it beats less percent of solution. Let's see the most optimal solution. So he is also like added of n0, that means this is the same as the prefix response array. Then this is a check function that he has. Then he is doing the same thing of creating this added extra and checking at each step. So this is the same complexity of order of n, and his low is means total is also accumulate of sum, and low is 0. So he has a complexity of n log into, means he has used low as 0, but we should have used low as minimum, so our complexity is better even if like his solution runs faster. So this doesn't matter like whether it beats 5% of or none, but because the complexity we know is like the most optimal. Okay, so I hope like the entire discussion was fruitful and you were able to learn something new out of it. And if you did, make sure to like as well as subscribe. And if you yet have any doubts remaining in any of the parts discussed or any of the new concepts discussed, then like make sure to revise this on like various blogs online. And if you yet have any doubts remaining, then make sure to comment down. I will be happy to respond. Thank you so much for watching.